Look up at the night sky. See those pinpoints of light, stars, clustered into galaxies, scattered across the darkness. Now focus on the darkness itself. The empty space between those islands of light. That emptiness is not empty. It contains something so vast, so fundamental, that understanding it changes everything we thought we knew about reality. The space between galaxies holds 80% of the universe's volume, yet we barely understand what fills. Scientists call these regions cosmic voids, but void is misleading. These spaces contain structure, energy, and mysteries that challenge physics itself. What actually exists in the space between galaxies? The answer is stranger than you can imagine. This is not just about empty space. This is about the hidden architecture of the cosmos, the architecture of nothing. Space is not a container. This is the first thing to understand. When we look at the gaps between galaxies, we imagine emptiness, a vacuum, nothingness stretching for millions of light years. But this intuition is completely wrong. Space itself is something. It has properties, structure, and behavior. The regions between galaxies are not simply absent of matter. They are active participants in cosmic evolution. The universe contains roughly 200 billion galaxies in the observable region alone. Each galaxy is an island of stars, typically containing 100 billion to 1 trillion stars. But the galaxies do not fill space uniformly. They cluster together in specific patterns. Between these clusters stretch enormous regions called voids. These voids are not randomly distributed. They form a cosmic web, a large-scale structure that defines the shape of the universe itself. This cosmic web was predicted theoretically before it was observed. In the 1,960 seconds and 1,970 seconds, cosmologists studying structure formation realized that matter should not be distributed uniformly. Gravity amplifies initial density variations. Regions slightly denser than average attract more matter. Regions slightly less dense lose matter to their neighbors. Over billions of years, this process creates extreme contrasts. Dense regions become filaments and clusters. Underdense regions become voids. The first observational evidence came in 1981 when astronomers discovered the Botez void. This was a spherical region roughly 330 million light-years across, containing far fewer galaxies than expected. Instead of the thousands of galaxies predicted by uniform distribution, they found only 60. The void was so empty that it seemed impossible. How could such a large region exist with so little inside it? Further observations revealed that Botez was not unique. Voids are everywhere. They make up the majority of the universe's volume. Galaxies and galaxy clusters occupy less than 20% of space. The remaining 80% consists of voids. These are not small bubbles. They are colossal structures. Typical voids measure 30 to 300 million light-years across. The largest known void, the giant void in the constellation Cetus, spans 1 billion light-years. Mapping these voids revealed something astonishing. They are not scattered randomly. They fit together like bubbles in foam. The cosmic web has a specific geometry. Dense filaments form the edges, where voids meet. Galaxy clusters sit at the nodes where multiple filaments intersect. Between them stretch the voids, nearly spherical regions of extreme underdensity. This structure is fractal-like. Similar patterns appear at different scales. Small voids within larger voids, filaments branching into smaller filaments. Understanding why this structure exists requires looking at the universe's history. In the beginning, immediately after the Big Bang, matter was distributed almost uniformly, almost quantum. Fluctuations during inflation created tiny density variations. Regions differed in density by only 1 part in 100,000. These fluctuations were random, but not completely. They had a specific statistical pattern determined by inflation's physics. As the universe expanded and cooled, gravity began amplifying these fluctuations. Denser regions attracted surrounding matter. They grew denser while depleting their surroundings. The underdense regions became voids. The overdense regions became the seeds of galaxy clusters. This process is called gravitational instability. It is the fundamental mechanism driving cosmic structure formation, but gravity alone does not fully explain the cosmic web's geometry. Dark matter plays a critical role. Simulations show that ordinary matter by itself would not create the observed structure. Dark matter provides the gravitational scaffolding. It collapses first, forming the web's basic framework. Ordinary matter follows, flowing along dark matter filaments toward nodes and clusters. Voids form naturally as matter drains from underdense regions into overdense ones. The cosmic web is not static, it evolves. In the early universe, the structure was more subtle. Voids were smaller and less empty. Filaments were thinner and less defined. Over billions of years, the contrasts increased. Voids expanded and emptied. Filaments contracted and accumulated more mass. This process continues today. The cosmic web is still growing, still evolving, still separating into denser and emptier regions. Measuring void properties is technically challenging. They are defined by absence, not presence. Astronomers must survey large volumes of space, mapping galaxy positions in 3 dimensions. The distance to each galaxy must be measured using redshift. This requires obtaining spectra for millions of galaxies. The first major surveys covered only small patches of sky. Modern surveys, like the Sloan Digital Sky Survey, have mapped hundreds of millions of galaxies across large fractions of the sky. These surveys reveal void statistics. The typical void is roughly spherical with a radius of about 50 million light-years. Voids are not completely empty. They contain a few galaxies, far fewer than expected from the average density. The void interior has roughly 10% of the average cosmic density. This means 90% of the matter that should be there is missing. It was pulled out by surrounding overdense regions. Void boundaries are not sharp. Density gradually increases as you move from void center to void edge. The transition region where density rises from 10% to average is called the void wall. This is where most void galaxies reside. Very few galaxies sit in the deepest void interiors. Those that do are unusual. They formed in an underdense environment and evolved differently from galaxies in DIS, normal regions. The emptiness of voids poses a puzzle. If they started with only slight underdensity, how did they become so empty? The answer involves multiple effects working together. Gravity pulls matter toward overdense regions. This creates bulk flows, large-scale motions of matter streaming toward filaments and clusters. These flows drain the voids. Additionally, the expansion of space is more noticeable in underdense regions, with less matter to resist. Expansion. Voids expand faster than average. This stretching further dilutes their already low density. Some voids appear to expand faster than the Hubble expansion rate. These are called supervoids. Their expansion accelerates the evacuating of remaining matter. Supervoids might be connected to dark energy. If dark energy density varies slightly from place to place, supervoids could be regions where dark energy's repulsive effect is slightly stronger. This remains speculative. Measuring dark energy's local variation is beyond current capabilities, but it represents a frontier in cosmology. Understanding why voids are so empty might reveal new physics. The geometry of the cosmic web is determined by initial conditions plus gravitational evolution, but the specific pattern we observe was not predetermined. It emerged from random quantum fluctuations during inflation. This means the cosmic web is fundamentally random on large scales. If we could observe a different region of the universe beyond our horizon, we would see a different pattern of voids and filaments. The same statistical properties, but different specific shapes and locations. This randomness has implications. The cosmic web cannot be predicted from first principles. We can only calculate its statistical properties. The web's specific configuration is a frozen accident determined by quantum fluctuations that occurred during inflation. Studying the web's geometry reveals information about those initial fluctuations. The web is a fossil record preserving data about the universe's first moments. Mathematically, the cosmic web can be described using percolation theory and topology. Percolation theory studies how connected structures emerge in random systems. The cosmic web percolates. Dense regions form a connected network of filaments spanning the universe. Voids form a complementary network of empty bubbles. These two networks interleave. Neither dominates completely. This balance creates the characteristic foam-like structure. Topologically, the cosmic web is complex. Filaments are one-dimensional structures threading through three-dimensional space. Walls, zero-dimensional, are two-dimensional points, where sheets, filaments, clusters are meet. Voids are three-dimensional bubbles. This hierarchy of dimensions creates rich structure. Characterizing it requires tools from differential geometry and algebraic topology. Recent work has applied persistent homology, a technique from topological data analysis, to quantify the web's structure mathematically. The cosmic web is not just interesting geometry, it has physical consequences. Matter flows along filaments toward clusters. This feeding process supplies raw material for galaxy formation. Galaxies forming in different environments evolve differently. Cluster galaxies experience frequent interactions, mergers, and tidal forces. Void galaxies evolve in isolation with minimal interactions. This environmental dependence shapes galaxy populations. Understanding the web is necessary for understanding galaxy evolution. The web also affects cosmic radiation, light traveling through. Voids experiences different gravitational potentials than light traveling through filaments. This creates slight temperature variations in the cosmic microwave background. Observing these variations, called the integrated Sachs-Wolf effect, provides independent evidence for void existence and properties. The effect is small but measurable. It confirms that voids are real, under dense regions, not just artifacts of galaxy distribution. What the cosmic web reveals is that structure is fundamental. The universe is not homogeneous on scales between galaxies and the cosmic horizon. Instead, it is highly structured, organized into a specific pattern. This pattern emerged naturally from simple initial conditions plus gravity. No designer needed, no special fine-tuning required, just quantum fluctuations, dark matter, gravity, and time. These ingredients inevitably produce the cosmic web we observe. But the web raises questions. Why are voids so empty? What exactly fills them? Is space truly continuous or discrete at the smallest scales? Does the void structure extend beyond our observable horizon? These questions push against the boundaries of current physics. Answering them requires understanding not just what exists between galaxies, but what existence itself means in the context of space, fields, and the vacuum, the substance of empty space. Quantum mechanics says empty space is not empty. This is a confirmed fact, not speculation. The vacuum, even in the deepest voids between galaxies, seethes with activity at microscopic scales. Virtual particles constantly pop into existence, exist briefly, then vanish. This happens everywhere, constantly, unavoidably. It is not a defect in our theories. It is a prediction of quantum field theory, verified by multiple experiments. The vacuum state is the lowest energy configuration of quantum fields. But lowest energy does not mean zero energy. Quantum uncertainty forbids fields from sitting perfectly still. Even in their ground state, fields fluctuate. These fluctuations are real, not just mathematical artifacts. They produce measurable effects. The Casimir effect demonstrates this directly. Place two uncharged metal plates close together in a vacuum. Quantum fluctuations of the electromagnetic field create a small, attractive force between them. This force has been measured with high precision. It matches quantum field theory predictions exactly. The force arises because certain wavelengths of virtual photons cannot fit between the plates. This reduces vacuum energy between the plates compared to outside. The energy difference creates pressure, pushing the plates together. The Casimir effect proves that vacuum fluctuations are real. They carry energy and momentum. They exert forces on physical objects. Empty space is not nothing. It is a quantum field in its ground state, fluctuating constantly. This applies everywhere, including the vast voids between galaxies. But vacuum fluctuations are not the only thing filling intergalactic space. Even voids contain small amounts of ordinary matter, mostly hydrogen and helium gas. The density is extraordinarily low, roughly 1 atom per cubic meter. For comparison, the best laboratory vacuum contains about 100,000 atoms per cubic centimeter. Intergalactic space is 1 trillion times less dense. Yet integrated over millions of light years, this matter adds up. The gas between galaxies is not uniformly distributed. It traces the cosmic web. Filaments contain more gas than voids. The densest gas sits in filament intersections where galaxy clusters form. This gas has a history. Some were never incorporated into galaxies. It has remained in intergalactic space since the early universe. Other gas was ejected from galaxies by supernovae and active galactic nuclei. These violent processes blow enriched gas into the intergalactic medium. Observing intergalactic gas is difficult. The density is too low for direct imaging in most cases. Instead, astronomers use absorption spectroscopy. Light from distant quasars passes through intervening gas. The gas absorbs specific wavelengths, creating dark lines in the quasar spectrum. These absorption lines reveal the gas's presence, density, temperature, and composition. By observing many quasars, astronomers map the intergalactic medium's distribution. This technique revealed the Lyman alpha forest. Quasar spectra show numerous absorption lines from neutral hydrogen. Each line corresponds to a cloud of gas between us and the quasar. The lines have different redshifts, indicating gas at different distances. The pattern of lines traces the large-scale structure. Dense regions produce strong absorption. Voids produce weak absorption, or none at all. The Lyman alpha forest is a one-dimensional probe of the three-dimensional cosmic web. The intergalactic medium is not cold. In filaments and clusters, the gas is shock-heated to millions of degrees. This happens when gas falls into the potential wells of large-scale structures. Gravitational energy converts to thermal energy. The hot gas emits X-rays. Observations from X-ray telescopes like Chandra XMM Newton detect this emission from massive galaxy clusters. X-ray brightness traces gas density. Maps show that clusters contain enormous reservoirs of hot gas, often outweighing the stars in galaxies. In voids, the gas is cooler and less ionized. It has not experienced significant shock heating because voids have shallow potential wells. The gas temperature in void centers is only a few thousand degrees. This is still much hotter than the cosmic microwave background temperature of 2.7 Kelvin, but it is cold compared to cluster gas. The cool void gas is harder to observe. It does not emit strong X-rays or radio waves. It reveals itself mainly through absorption lines. The intergalactic medium contains most of the normal matter in the 5 galaxies. Galaxies and stars account for only about 10% of the baryons. The remaining 90% resides in the diffuse gas between galaxies. This gas is the raw material for future star formation. As it slowly falls into galaxies, it replenishes their gas supplies. Without this reservoir, star formation would cease as galaxies exhaust their internal gas. Dark matter also fills intergalactic space. In fact, dark matter dominates. For every kilogram of normal matter, there are roughly 5 kilograms of dark matter. Dark matter does not emit, absorb, or scatter light. It interacts only gravitationally. This makes it invisible but not undetectable. Its gravitational effects are measurable through multiple methods. Gravitational lensing reveals dark matter's distribution. Massive structures bend light from background sources. This bending, predicted by general relativity, acts like a lens. It distorts and magnifies background galaxies. The amount of distortion depends on the foreground mass. By measuring distortion statistically across large areas, astronomers map dark matter distribution. These maps show that dark matter traces the cosmic web. Filaments contain dark matter. Voids contain very little. The cosmic web's skeleton is made of dark matter. Normal matter follows the dark matter distribution. Galaxies form where dark matter density is high. Voids form where dark matter density is low. This is confirmed by comparing gravitational lensing maps with galaxy surveys. The two distributions match closely. Dark matter defines the structure. Normal matter fills it in. Simulations of cosmic structure formation require dark matter. Without the simulated universe looks nothing like observations. With it, simulations reproduce the cosmic web in remarkable detail. The match between simulation and observation is one of cosmology's great successes. It confirms that dark matter exists and that it behaves gravitationally as theory predicts. But we still do not know what dark matter is. The leading candidates are weakly interacting massive particles, or WIMPs. These hypothetical particles would have been created in the early universe. They would interact only through gravity and possibly the weak nuclear force. Experiments have searched for them using extremely sensitive detectors deep underground. So far, no confirmed detection. Other candidates include axions, sterile, neutrinos, and primordial black holes. Each has different properties and detection methods. The dark matter problem remains unsolved. Dark energy is even more mysterious. It fills all of space, including voids. In fact, dark energy dominates void properties. The energy density of dark energy is constant throughout space and time. This is called the cosmological constant model. Dark energy makes up 68% of the universe's total energy content. Dark matter is 27%. Normal matter is only 5%. Space itself, even completely empty space, contains energy. Dark energy has negative pressure. This is a bizarre property with no everyday analogue. Negative pressure acts like anti-gravity. Instead of pulling things together, it pushes them apart. This creates the accelerating expansion observed in distant supernovae. Galaxies are not just moving apart, they are accelerating away from each other. The expansion rate is increasing over time. In voids, dark energy dominates completely. Normal matter and dark matter are negligible. The void's evolution is determined almost entirely by dark energy. This makes voids sensitive probes of dark energy properties. By measuring void expansion rates and shapes, cosmologists can test models of dark energy. Current observations are consistent with a cosmological constant, but the uncertainty is large enough that other models remain viable. What is dark energy? Nobody knows. The simplest explanation is that it is vacuum energy, the ground state energy of quantum fields. Quantum field theory predicts that vacuum should have energy, but the predicted value is 10^120 times larger than observed. This is the cosmological constant problem, one of the worst prediction failures in physics. Why is vacuum energy so small? No accepted answer exists. Alternative explanations propose new fields or modifications to gravity. Quintessence is a hypothetical field with negative pressure. Unlike a cosmological constant, quintessence can vary in space and time. This would create testable differences in void properties and cosmic expansion history. Modified gravity theories, like MUND or FR gravity, attempt to explain accelerating expansion without dark energy. These theories modify general relativity at large scales. Distinguishing between models requires precise measurements of cosmic structure and expansion. The vacuum also contains magnetic fields. These fields are weak, typically 1/1,000,000th the strength of Earth's magnetic field, but they extend over enormous distances. Intergalactic magnetic fields thread through the cosmic web. Their origin is uncertain. Some might be primordial, created in the early universe. Others might be expelled from galaxies along with gas. Still others might be generated by turbulent plasma flows in the intergalactic medium. Measuring intergalactic magnetic fields is challenging. The fields are too weak to detect directly. Instead, astronomers use indirect methods. Fast radio bursts, brief flashes of radio waves from distant galaxies experience Faraday rotation as they travel through magnetized plasma. The rotation amount reveals the strength and direction of intervening magnetic fields. Observations suggest typical field strengths around 10⁻16 Gauss. This is extremely weak but significant when integrated over cosmological distances. Cosmic rays also fill intergalactic space. These are high-energy particles, mostly protons, accelerated to near light speed. They originated in supernovae, active galactic nuclei, or other violent cosmic events. Cosmic rays are charged, so magnetic fields deflect. Most cosmic rays we detect originated within our galaxy, but the highest energy cosmic rays have energies so high that galactic magnetic fields cannot contain them. These ultra-high energy cosmic rays must come from extragalactic sources. The most energetic cosmic rays ever detected have energies exceeding 10-20 electron volts. That is the kinetic energy of a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. The origin of these particles is unknown. They cannot travel far before losing energy to interactions with the cosmic microwave background. This limits their range to a few 100 million light-years. Whatever accelerates them must be relatively nearby. Possibilities include active galactic nuclei, gamma-ray bursts, or more exotic sources. Neutrinos also permeate intergalactic space. These ghostly particles interact only weakly with matter. Trillions pass through your body every second without effect. Neutrinos produced in the Big Bang filled the universe with a cosmic neutrino background, analogous to the cosmic microwave background. These relic neutrinos have cooled to about 1.9 Kelvin. They have never been directly detected because their interaction probability is so low, but they must exist. They affect cosmic structure formation by suppressing small-scale matter clumping. Gravitational waves also propagate through intergalactic space. These ripples in space-time travel at light speed. They are produced by accelerating masses, especially violent events like black hole mergers or neutron-star collisions. Gravitational waves pass through matter almost undisturbed. This makes them excellent messengers carrying information about distant cataclysms. Recent detections by LIGO and Virgo have opened gravitational wave Astronomy. Future space-based detectors like LISA will observe lower frequency waves from supermassive black hole mergers. The list of what fills empty space is long. Virtual particles from quantum fluctuations, sparse neutral gas, hot ionized plasma, dark matter, dark energy, magnetic fields, cosmic rays, neutrinos, gravitational waves, photons at all wavelengths. The space between galaxies is not empty. It contains multiple components with different properties and behaviors. Some interact electromagnetically, some only gravitationally, some not at all, except through the weak force. Each component has its own distribution and evolution. Together, they form the intergalactic medium, a complex multi-phase system. Understanding this system requires combining observations across the electromagnetic spectrum, from radio through gamma rays, plus non-electromagnetic messengers like neutrinos and gravitational waves. No single observation type captures the full picture. Only by integrating multiple datasets can astronomers reconstruct what truly exists in the space between galaxies. This space is not inert, it is dynamic. Gas flows along filaments toward clusters. Magnetic fields amplify through dynamo processes. Cosmic rays propagate and interact. Dark energy drives, accelerating expansion. The intergalactic medium evolves. It was different in the past. It will be different in the future. The voids we observe today are snapshots of an ongoing cosmic evolution. Understanding them requires understanding their history and the processes shaping them. The vacuum itself might have structure at the deepest levels. Quantum gravity theories propose that space-time is not continuous, but discrete at the Planck scale, 10⁻⁻35 meters. At this scale, space might be a quantum foam, fluctuating wildly, or it might be a network of discrete elements, loops or spin networks, building up smooth space at larger scales. These ideas remain speculative. Testing them requires probes at energies far beyond current capability, but they suggest that even the concept of empty space might be incomplete. Space itself might be made of something more fundamental. What fills the space between galaxies is therefore a layered answer. At macroscopic scales, diffuse gas and dark matter. At intermediate scales, fields and particles. At quantum scales, vacuum fluctuations. At the deepest scales, possibly a discrete structure not yet understood. Each layer contributes, each is real. The space between galaxies is not a void, it is a complex, structured, evolving medium. Understanding it is understanding the universe itself, the temperature of darkness. Space is cold, this seems obvious. The distance from any warming star means temperatures should approach absolute zero, but cold is relative, and the space between galaxies is not as cold as we might think. It has a definite temperature, shaped by invisible energy sources spread across the cosmos. The coldest possible temperature is absolute zero, or 0 Kelvin, where all molecular motion ceases. Classical physics says nothing could be colder, but quantum mechanics disagrees. Even at the lowest temperature, quantum fluctuations remain. The universe always carries a faint hum of zero-point energy that prevents true stillness. The cosmic microwave background sets the temperature floor everywhere. This radiation fills all of space uniformly, a relic from the moment the universe became transparent 380,000 years after the Big Bang. Before that, light could not travel freely. When atoms formed, photons were released, and those same photons have been traveling ever since. The universe's expansion has stretched their wavelengths, cooling the radiation from 3000 Kelvin to 2.725 Kelvin today. Every cubic centimeter of space holds about 400 of these ancient photons, forming a universal bath of microwave light. Any object not heated by nearby stars will cool until it reaches this same equilibrium. Gas, dust, and even rogue planets drift in, balance with the cosmic microwave background. In the vast voids between galaxies, far from any light source, the dominant temperature is this cosmic minimum, about 2.7 Kelvin. Yet intergalactic space is not uniformly cold along filaments and in galaxy clusters. Gas is shock-heated to millions of degrees. As matter falls into deep gravitational wells, its kinetic energy converts to heat. Clusters glow in X-rays as hot plasma radiates. Energy through bremsstrahlung, or breaking radiation. The hottest gas sits in cluster cores, reaching tens of millions of Kelvin. This heating comes primarily from gravity, not from stars or galaxies. Between clusters lie filaments, bridges of matter connecting galaxies. The gas there is much warmer than voids, but cooler than fixed clusters, reaching between 100,000 and 1 million Kelvin. Observations through X-ray and ultraviolet absorption confirm that these filaments form part of the cosmic web, tracing the same structure as galaxies and dark matter. Cooling works alongside heating. Hot gas radiates energy over time. In dense regions, this cooling can be rapid, allowing gas to condense and form stars. But in galaxy clusters, observations reveal less cooling than theory predicts. This cooling flow problem is solved by feedback from active galactic nuclei, jets. From supermassive black holes, inject energy into the surrounding gas, offsetting cooling and maintaining high temperatures. X-ray images show vast cavities where black hole jets have pushed hot plasma aside, balancing energy loss and gain. Even in the emptiest voids, faint heating persists. Starlight and quasars emit ultraviolet radiation that ionizes hydrogen gas, keeping it slightly warmer than the background. This gentle photoionization lifts void temperatures to around 10,000 Kelvin. The voids, though dark and quiet, still hum with energy left over from ancient stars. The Sunyaev-Zeldovich effect provides another way to study cosmic temperatures. When cosmic microwave background photons pass through hot gas, they scatter off energetic electrons, gaining energy in the process. This distorts the CMB spectrum slightly in the direction of galaxy clusters. Measuring this distortion allows astronomers to map hot gas without relying on X-ray light, extending detection to distant clusters. Across space, temperature reflects the universe's structure. Cold voids mark the shallows of gravity. Warm filaments trace the threads of the cosmic web. Hot clusters reveal the deepest gravitational wells. Together, they form a cosmic temperature map showing how energy flows and structures form across billions of light years. The darkness between galaxies is therefore not uniformly cold. It holds gradients of heat shaped by gravity, radiation, and expansion. Each variation tells a piece of the universe's story, showing how matter collapsed, how light scattered, and how energy shaped the vastness of the cosmic void. The transit of light. Light does not travel instantaneously. It has a speed 299,792,458 meters per second in vacuum. This is the universe's ultimate speed limit. Nothing can travel faster. This finite speed means that light takes time to cross intergalactic distances, and during that journey, multiple things happen to the light. Understanding these effects reveals fundamental properties of the space between galaxies. The most obvious effect is time delay. Light from distant galaxies takes millions or billions of years to reach us. When we observe a galaxy 100 million light years away, we see it as it was 100 million years ago. The light has been traveling through space for that entire duration. This creates a cosmic time machine. Telescopes are instruments for observing the past. The farther we look, the further back in time we see. This time delay applies to all electromagnetic radiation, not just visible light. Radio waves, infrared, X-rays, gamma rays, all travel at the same speed in vacuum. They all experience the same time delay. This is a prediction of special relativity confirmed by countless experiments. The speed of light is constant, regardless of wavelength or photon energy. It is a fundamental constant of nature, but light does not travel through a perfect vacuum. The space between galaxies contains matter, fields, and radiation. These create interactions that modify light as it travels. The most important effect is cosmological redshift. As the universe expands, it stretches the wavelengths of photons traveling through space. A photon emitted as blue light might arrive as red light. A photon emitted as ultraviolet might arrive as infrared. This redshift is not a Doppler effect in the usual sense. The source is not moving through space. Space itself is expanding, carrying the source and observer apart. The photon's wavelength stretches along with space. This is called cosmological redshift, to distinguish it from velocity-induced Doppler shift. Though mathematically similar at low speeds, the physical cause is different. Expansion of space rather than motion through space. Redshift is quantified by the parameter z, defined as the change in wavelength divided by the original wavelength. A redshift of z equals 1 means wavelengths have doubled. The universe has expanded by a factor of 2 since the light was emitted. Current telescopes detect galaxies with redshifts exceeding z equals 10. These galaxies existed when the universe was less than 500 million years old. Their light has been travelling for over 13 billion years. The wavelengths have stretched by a factor of 11. Redshift affects all photon properties, not just wavelength, but also energy and momentum. A photon with energy E, when emitted, has energy E 1 plus Z when received. The energy loss is not a violation of conservation laws. The expansion of space does work against the photon, extracting energy. This energy goes into the expansion itself. It is not lost but transformed into the increasing separation between source and observer. The cosmic microwave background provides the most dramatic example. These photons started as visible and UV light with wavelengths around 1 micrometer. After 8 billion years of expansion, the wavelengths have stretched to about 1 millimeter, a factor of 1,000 increase. The redshift is Z equals 1089. The universe has expanded 1090 times since recombination. The photons have cooled from 3000 Kelvin to 2.725 Kelvin. Their energy is 1090 times lower than when emitted. But redshift is not the only effect. Absorption can remove photons entirely. Intergalactic gas, though sparse, contains atoms and ions. These absorb photons at specific wavelengths corresponding to atomic transitions. Hydrogen is most important because it is the most abundant element. Neutral hydrogen strongly absorbs ultraviolet light at 121.6 nanometers, the Lyman alpha transition. Ionized hydrogen does not absorb at this wavelength, but can absorb higher energy photons that ionize it further. When light from a distant quasar travels through intergalactic space, it encounters many clouds of hydrogen gas. Each cloud absorbs light at the Lyman alpha wavelength as measured in the cloud's rest frame. But because of redshift, different clouds are at different distances and have different recession velocities. Each cloud absorbs at a different observed wavelength. The result is a forest of absorption lines in the quasar spectrum, the Lyman alpha forest. This forest reveals the distribution of neutral hydrogen along the line of sight. Dense gas clouds produce strong absorption, diffuse. Gas produces weak absorption. Voids produce almost no absorption. By observing many quasars in different directions, astronomers map the three-dimensional distribution of intergalactic gas. The resulting map traces the cosmic web. Filaments show as regions with many absorption lines. Voids show as regions with few. Other elements also produce absorption lines. Helium, carbon, oxygen, silicon, iron, all leave characteristic signatures. These metal lines reveal that intergalactic gas is enriched. It is not pristine primordial gas. It contains elements created in stars and expelled by supernovae. The enrichment pattern tells us about galactic winds, metal transport, and the efficiency of star formation in galaxies. Absorption is not the only interaction. Scattering can also affect light. The most important scattering process in intergalactic space is Thomson scattering. Free electrons scatter photons elastically. The photon direction changes, but the energy is essentially preserved in the electron's rest frame. This process created the cosmic microwave background surface of last, scattering at recombination. Before that, photons scattered constantly. Afterwards, scattering became rare because most electrons were bound in atoms, but the universe was reionized by the first stars and galaxies. Today, most intergalactic hydrogen is ionized. Free electrons exist throughout space, though at very low density. These electrons scatter CMB photons. Not frequently, but occasionally. The probability that a given CMB photon scattered since recombination is about 5%. This rescattering slightly blurs the CMB's primary anisotropies. It erases structure on small, angular scales while leaving large scales intact. Thomson scattering also creates the Sunyaev-Zeldovich effect discussed earlier. Hot electrons in galaxy clusters scatter CMB photons, boosting their energy. This creates a distinctive spectral distortion. The effect is small but measurable. It provides a way to detect and study clusters without relying on X-ray emission. The SZ effect is a direct probe of intracluster gas temperature and density. Gravitational lensing affects light in a different way. Mass bends space-time. Light follows geodesics, the straightest possible paths through curved space-time. When light passes near a massive object, its path curves. This deflection is a prediction of general relativity, famously confirmed during the 1919 solar eclipse. The effect is small for individual stars, but for galaxies and galaxy clusters, it becomes significant. Strong lensing creates multiple images of background sources. If a foreground galaxy is perfectly aligned with a background quasar, the quasar's light is bent into a ring called an Einstein ring. More typically, alignment is not perfect. Multiple distorted images appear around the lensing galaxy. These lensed images reveal the foreground mass distribution. By modeling the lensing, astronomers map dark matter. This works even if the foreground mass is invisible. Lensing responds to all mass, dark or luminous. Weak lensing creates subtle distortions in galaxy shapes. No, multiple images form. Instead, background galaxies are slightly stretched tangentially around foreground masses. This stretching is called shear. It is tiny, only a few % distortion, but it is statistically detectable. By measuring the shapes of millions of background galaxies, astronomers map the large-scale matter distribution. This includes dark matter in filaments and voids. Weak lensing surveys have mapped dark matter across large areas of the maps show the cosmic web. Filaments appear as regions of enhanced lensing. Voids appear as regions of reduced lensing. These maps are independent of galaxy surveys. They trace matter directly, not just where light is emitted. Comparing lensing maps to galaxy distributions, tests, structure formation models, the agreement is excellent, confirming that galaxies trace the underlying dark matter distribution. Gravitational time delay is another lensing effect. Light taking different paths around a lens travels different distances through different gravitational potentials. General relativity predicts that these paths have different travel times. If a lensed quasar varies in brightness, the variations appear at different times in different images. The time delays range from days to years, depending on lens mass and geometry. Measuring time delays allows determination of the Hubble constant. The time delay depends on distances and cosmic expansion rate. By observing multiple lensed quasars and measuring their time delays, astronomers can constrain the Hubble constant independently of other methods. This is important because different measurement techniques give slightly different values. The discrepancy is called the Hubble tension. Lensing time delays might help resolve it. Magnetic fields also affect light propagation. Intergalactic magnetic fields are weak but ubiquitous. Light itself is unaffected because photons are uncharged. But polarized light experiences Faraday rotation. The plane of polarization rotates as light passes through magnetized plasma. The rotation angle depends on field strength plasma density, and path length. Measuring this, rotation reveals magnetic field properties. Fast radio bursts are particularly useful for this purpose. These mysterious millisecond duration radio pulses come from distant galaxies. As the radio waves travel through intergalactic space, they experience Faraday rotation. The rotation measure reveals the integrated magnetic field strength along the line of sight. Observations show typical intergalactic field strengths around 10^-16 Gauss. This is extremely weak but significant over cosmological distances. Dispersion is another effect affecting radio waves. Ionized gas has a frequency-dependent refractive index. Lower frequency waves travel slightly slower than higher frequency waves. This causes pulses to spread out in time. The amount of spreading depends on the integrated electron density along the path. This is called the dispersion measure. By measuring dispersion of fast radio bursts, astronomers trace ionized gas distribution. Pair production can absorb very high energy gamma rays. When a gamma ray photon with energy above 1 TeV propagates through intergalactic space, it can interact with background photons to create electron-positron pairs. This process absorbs the gamma ray. The probability increases with gamma ray energy and path length. Observations of distant gamma ray sources show an energy cutoff at high energies due to this absorption. The absorption depends on the density of background photons. The cosmic microwave background is one source. The extragalactic background light, infrared photons from all galaxies throughout. Cosmic history is another. Measuring gamma ray absorption as a function of source distance reveals the extragalactic background, light intensity. This probes the total star formation history of the universe. Every star ever formed contributed photons to this. Background. Neutrino propagation is different. Neutrinos interact only weakly with matter. They pass through intergalactic gas almost undisturbed. A neutrino can traverse the entire observable universe without interacting. This makes neutrinos excellent messengers from distant sources, but it also makes them extremely difficult to detect. Massive detectors containing thousands of tons of water or ice are needed to catch rare neutrino interactions. Gravitational waves also propagate unimpeded. Like neutrinos, they interact only weakly with matter, but they carry different information. Gravitational waves are produced by accelerating masses, especially compact objects like black holes and neutron stars. A merger event in a distant galaxy produces gravitational waves that propagate outward at light speed. These waves pass through galaxies, gas, and dust. Without attenuation, they reach us, carrying pristine information about the source. The combination of multiple messengers revolutionizes astronomy. Observing an event simultaneously in electromagnetic radiation, neutrinos, and gravitational waves provides comprehensive information. This is called multi-messenger astronomy. The 2017 neutron star merger GW170817 was observed in all three channels. Gravitational waves revealed the masses and orbital evolution. Gamma rays showed a relativistic jet, optical and infrared. Observations tracked the kilonova, the radioactive glow from newly synthesized heavy elements. The space between galaxies is not just passive, it is an active, optical medium. It redshifts, absorbs, scatters, lenses, rotates, disperses, and delays light. Each effect reveals different properties. Redshift reveals expansion history. Absorption reveals gas distribution. Scattering reveals electron density. Lensing reveals mass distribution. Rotation reveals magnetic fields. Dispersion reveals ionization. Each effect carries information encoded in light that has traveled for millions or billions of years. Studying these effects requires precise spectroscopy and photometry. Modern instruments can measure redshifts to 1 part in 100,000. This precision reveals subtle features in spectra. Absorption line strengths constrain gas density and temperature. Emission line ratios reveal ionization state. Continuum slopes indicate dust extinction. Every detail matters. Every photon carries data. The transit of light through intergalactic space is therefore not just a journey. It is a measurement process. The light interacts with everything it encounters. Each interaction modifies the light in specific ways. By the time photons reach our telescopes, they carry an encoded history of their journey. Decoding that history reveals the properties of intergalactic space. The gas, dust, magnetic fields, matter distribution, expansion rate, all leave fingerprints in the light. This is why astronomy is possible. Light is both messenger, probe. It travels vast distances carrying information. It interacts with its surroundings in predictable ways. By observing light from distant sources and analyzing how it has been modified, we reconstruct the properties of space it traversed. The darkness between galaxies reveals itself through the light that crosses it. The hidden connections. Galaxies are not isolated islands. They are connected through multiple channels. Gas flows between them. Stars escape from them. Gravitational forces link them across vast distances. These connections are subtle but real. They shape galaxy evolution and structure the cosmic web. Understanding these hidden connections reveals that the space between galaxies is not just empty separation. It is an active medium facilitating interactions. The most direct connection is gravitational. Every galaxy pulls on every other galaxy. The force decreases with distance squared, but it never disappears completely. For nearby galaxies, gravitational forces are strong enough to create bound groups and clusters. The local group contains the Milky Way, Andromeda, and about 80 smaller galaxies. All are gravitationally bound. They orbit their common center of mass. Eventually, over billions of years, many will merge. Gravitational interactions change galaxy trajectories. When two galaxies pass close, tidal forces deform them. Stars are pulled from their original orbits. Long tidal tails stretch out behind each galaxy. These tails can contain millions or billions of stars. They extend for hundreds of thousands of light years into intergalactic space. Some tidal features are so extensive that they bridge the gap between galaxies. The Magellanic Stream is a spectacular example. This is a gaseous structure stretching more than 200 degrees across the sky. It consists of neutral hydrogen stripped from the Magellanic Clouds by tidal forces during their interaction with the Milky Way. The stream contains roughly 200 million solar masses of gas. It extends for nearly 500,000 light years. wrapping around the Milky Way. This is a direct physical connection between galaxies, a bridge of gas linking them. Other galaxies show similar features. M31 and M33 in the local group are connected by a bridge of hydrogen gas. The antennae, Galaxies, two spirals in the process of merging, have tidal tails, extending 300,000 light-years. These tails contain young star clusters formed from gas compressed during the interaction. The tails will eventually fall back into the merged system, but for now they exist in intergalactic space. Tidal features reveal interaction histories. By modeling tidal tail orbits, astronomers reconstruct past encounters. The stars in tidal tails are like tracer particles recording gravitational forces. Their current positions and velocities constrain the mass, distributions, and orbital parameters of the interacting galaxies. This technique has revealed that the Milky Way has been cannibalizing smaller galaxies throughout its history. Stellar streams in the galactic halo are remnants of disrupted dwarf galaxies. Galaxies also exchange gas through galactic winds. Supernovae and active galactic nuclei drive powerful outflows. Gas is heated to millions of degrees and expelled at speeds of hundreds to thousands of kilometers per second. This gas escapes the galaxy and enters intergalactic space. Some escape entirely, other gas falls back in a galactic fountain, cycling between disk and halo on timescales of hundreds of millions of years. The expelled gas is enriched with heavy elements synthesized in stars: carbon, oxygen, silicon, iron, all produced by nuclear fusion and supernova nucleosynthesis. When this gas mixes with pristine intergalactic gas, it changes the composition. Observations show that even diffuse intergalactic gas contains metals. The enrichment is higher near galaxies and lower in voids, but even the deepest voids show some enrichment. Metals have been distributed remarkably uniformly. This metal distribution reveals that galactic winds can travel large distances. Simulations show that winds from galaxies can transport enriched gas across millions of light-years. The gas cools as it expands, eventually mixing with surrounding material. Some winds are so powerful that they create superbubbles, expanding shells of hot gas that displace the ambient medium. These bubbles can grow to sizes exceeding 100,000 light-years before fragmenting and dissipating. Galaxy clusters contain especially powerful winds. The intracluster medium is enriched to roughly 1/3 solar metallicity. This represents an enormous amount of processed material. All cluster galaxies have contributed gas over billions of years. Central galaxies with active galactic nuclei drive the most powerful winds. Jets from supermassive black holes plow through the intracluster medium, creating cavities and shock waves. These jets can transport energy and metals across millions of light-years. Ram pressure also strips gas from galaxies. When a galaxy moves through the intracluster medium, the gas experiences pressure like a car moving through air. If the galaxy moves fast enough, this ram pressure exceeds the galaxy's gravitational binding force. Gas is stripped from the outer regions and left behind as a trail. These trails, called jellyfish structures, extend for hundreds of thousands of light-years. The stripped gas mixes with the intracluster medium, adding mass and metals. Star formation in intergalactic space is rare but not impossible. Tidal tails sometimes contain young star clusters. The gas in tidal tails was compressed during the interaction, triggering collapse and star formation. These clusters are not gravitationally bound to any galaxy. They orbit in intergalactic space, orphaned by the interaction that created them. Over time, they will disperse as individual stars follow independent orbits. Hypervelocity stars also travel through intergalactic space. These are stars ejected from galaxies at such high speeds that they escape completely. Several mechanisms can produce hypervelocity stars. Close encounters with supermassive black holes in galactic centers can slingshot stars outward. Supernova explosions in binary systems can kick the companion star to high velocity. Three-body interactions in dense star clusters can eject one member at escape velocity. Hundreds of hypervelocity stars have been discovered in the Milky Way's halo, traveling outward at 300 to 700 kilometers per second. These speeds exceed the Milky Way's escape velocity. The stars will eventually leave the galaxy entirely and enter intergalactic space. They will spend the rest of their lives as intergalactic wanderers, isolated from any galaxy. As they age, they will enrich intergalactic space nucleosynthesis with elements produced through cosmic rays. Also connect galaxies. These high-energy particles are produced in supernovae, supernova remnants, and active galactic nuclei. Cosmic rays are charged, so magnetic fields deflect them, but the highest energy cosmic rays have so much momentum that even galactic magnetic fields cannot contain them. They escape into intergalactic space and propagate through the cosmic web. Magnetic fields in intergalactic space deflect them, but weakly. The highest energy cosmic rays can travel across tens of millions of light years before losing energy. Detecting cosmic rays from specific extragalactic sources is challenging. Lower energy cosmic rays are deflected too much by magnetic fields. Their arrival directions do not point back to their sources. Only the highest energy cosmic rays, above 1019 electron volts, retain some directional information. Observations show weak correlations between ultra-high energy cosmic rays and nearby active galactic nuclei. This suggests AGN are sources, though the evidence is not yet conclusive. Neutrinos provide another connection. Supernova explosions release vast numbers of neutrinos. A core collapse supernova emits 1058 neutrinos over a few seconds. These neutrinos carry away 99% of the explosion's energy. They stream outward at light speed, passing through the star and entering intergalactic space. Most escape unimpeded. A tiny fraction interacts with matter, creating detectable signals. Supernova 1987A in the Large Magellanic Cloud produced neutrinos, detected on Earth. About 25 neutrinos were observed in detectors. Despite the event occurring 168,000 light-years away, this confirmed supernova theory and demonstrated neutrino astronomy's feasibility. Future galactic supernovae will produce thousands or millions of detected neutrinos, information about core collapse physics, providing unprecedented. Neutrinos from extragalactic sources are harder to detect because of greater distances and lower fluxes. But IceCube, a neutrino detector embedded in Antarctic ice, has detected high energy neutrinos from distant active galactic nuclei. These detections prove that AGN accelerates particles to extreme energies. The neutrinos produced in these accelerators travel through intergalactic space without deflection, pointing directly back to their sources. Gravitational waves also connect distant galaxies. Black hole mergers and neutron star mergers produce gravitational radiation detectable across cosmological distances. LIGO and Virgo have detected dozens of mergers. Most sources are within a few billion light years, but future detectors will reach farther. Gravitational waves carry information about masses, spins, orbital evolution. They reveal the population of compact objects in galaxies throughout cosmic history. The multi-messenger connections between galaxies are only beginning to be explored. Each type of messenger carries different information. Electromagnetic radiation reveals visible and energetic processes. Neutrinos reveal nuclear reactions. Cosmic rays reveal particle acceleration. Gravitational waves reveal extreme gravity. Combining these messengers provides a comprehensive picture of cosmic events and their impacts on intergalactic space. Dark matter also connects galaxies, though invisibly. The cosmic web's filaments are primarily dark matter. Galaxies form where dark matter density is highest. But the dark matter extends beyond galaxy boundaries. Dark matter halos surround galaxies, extending far into intergalactic space. These halos overlap, creating continuous dark matter structures spanning millions of light years. Galaxies are embedded in and gravitationally bound to this dark matter framework. Simulations show that dark matter halos have complex substructures. Within a large halo, smaller subhalos orbit. These subhalos may or may not contain visible galaxies. If they do, we observe them as satellite galaxies. If not, they remain invisible, detectable only through gravitational effects. The local group's dark matter halo likely contains hundreds of subhalos, but we observe only about 80 galaxies. The missing subhalos might be there, just too dark to see. This suggests that intergalactic space contains dark galaxies, concentrations of dark matter and gas without stars. These objects would be nearly impossible to detect except through gravitational lensing or rare gas absorption. A few candidates have been found. Clouds of hydrogen gas with no associated stars or optical emission. These might be primordial dark galaxies that never formed stars efficiently, or they might be remnants of interactions, gas stripped from galaxies and left behind. The connections between galaxies make the universe a coherent system. Galaxies do not evolve in isolation. They interact continuously with their environment and neighbors. Gas flows in and out. Stars escape. Radiation propagates. Particles stream through space. Gravitational forces shape trajectories. Each galaxy is a node in a network of connections. The space between galaxies is the medium through which these connections operate. Understanding these connections requires a multi-scale approach. At the smallest scales, individual stars and gas clouds interact with local radiation fields and magnetic structures. At intermediate scales, galactic winds and tidal forces redistribute matter. At the largest scales, the cosmic web determines gravitational potentials and matter inflow patterns. All scales, coupled together, local processes affect large-scale structure. Large-scale forces shape local evolution. The hidden connections between galaxies are gradually being revealed through better observations and more sophisticated simulations. Each new detection of a tidal stream, wind outflow, cosmic ray, neutrino, or gravitational wave adds to the picture. The space between galaxies is not a passive void. It is an active, structured, dynamically evolving medium. It connects, transports, transforms. It is as integral to the universe as the galaxies themselves. This realization changes how we study cosmic evolution. We cannot understand galaxies in isolation. We must understand the intergalactic medium, the cosmic web, the filaments and voids, the gas flows and radiation fields. Everything is connected. The universe is one system with many components interacting. The darkness between galaxies is where many of these interactions occur. It is the stage on which cosmic evolution plays out. The future of the voids. The universe is not static. It evolves. The voids we observe today are not the voids of the past or the future. They change as the universe ages. Understanding this evolution reveals the cosmos's ultimate fate. The future of the voids is the future of space itself. Today, the universe is 13.8 billion years old. It is in a phase of accelerating expansion driven by dark energy. Galaxies are moving apart, carried by expanding space. But this expansion is not uniform. Dense regions like galaxy clusters resist expansion through gravity. Their internal space does not expand significantly, but voids with minimal mass expand freely. In fact, voids expand faster than the average Hubble flow. They are growing. Measurements confirm this. Studies comparing void sizes at different cosmic times show that voids were smaller in the past. The median void radius has increased by roughly 50% over the last 7 billion years. This growth is expected from simulations as the cosmic web evolves. Overdense regions accrete matter from their surroundings. Underdense regions lose matter. The contrast increases. Voids become emptier and larger. Filaments and clusters become denser and more massive. This trend will continue. Over the next billions of years, voids will keep expanding and emptying. Galaxies on void edges will be pulled toward filaments. The few galaxies inside voids will become increasingly isolated. Eventually, void galaxies will lose all interaction with the rest of the universe. Light from distant galaxies will redshift beyond detectability. The cosmic microwave background will cool below measurability. Void galaxies will see only darkness. But this isolation is temporary in cosmic terms. Dark energy, if it remains constant as a cosmological constant, drives expansion indefinitely. All structures not gravitationally bound will eventually move beyond causal contact. Galaxy clusters will be the largest bound structures. Everything else will separate in roughly 150 billion years. The local group's few dozen galaxies will be all we can observe. The rest of the universe will have receded beyond the cosmic event horizon. At that time, observers in the Milky Way Andromeda Merger remnant will see a very different universe. No distant galaxies, no cosmic microwave background, no evidence of the Big Bang or cosmic expansion. They will observe a small, static, isolated island of light surrounded by infinite darkness. They will have no way to deduce the true nature of the cosmos. All evidence will have receded beyond reach. This is the informational future of voids writ large. As expansion continues, regions separate beyond information exchange. The universe fragments into causally disconnected patches. Each patch contains its own observable universe, contracting as expansion accelerates. Eventually, each patch sees only itself. No external information enters. No signals escape. The cosmos becomes a collection of isolated bubbles, each unaware of the others. But physical evolution continues within each bubble. Stars age and die. The last stars will exhaust their fuel in roughly 100 trillion years. After that, no more star formation occurs. Galaxies become dark graveyards of stellar remnants, white dwarfs, neutron stars, black holes. These remnants drift through space, occasionally colliding and merging, but no new light is created. The voids during this era will be truly empty. No galaxies, no light, just diffuse dark matter and dark energy. The expansion continues, stretching space without limit. The distance between any 2 points increases exponentially. This is the de sitter phase, where dark energy dominates completely. Space becomes asymptotically empty. If protons decay, as predicted by some grand unified theories, then even stellar remnants dissolve. Proton decay timescales are uncertain but estimated around 10-40 years if this happens. White dwarfs and neutron stars gradually evaporate into radiation and lighter particles. Only black holes remain as stable structures, but they too are temporary. Black holes evaporate through Hawking radiation. This process is extraordinarily slow for large black holes. A solar mass black hole takes 1067 years to evaporate. A supermassive black hole with 1 billion solar masses takes 100 years. But eventually, all black holes disappear. They radiate their mass away as photons and particles. The final burst, when the black hole shrinks to Planck scale, releases the remaining energy in a flash of gamma rays. After all, black holes evaporate around 100 years to the universe. Contains only radiation and elementary particles. The temperature is infinitesimally close to absolute zero. The particle density is infinitesimally low. Space continues expanding. The universe has reached maximum entropy. No structure remains. No gradients exist. Nothing can happen. This is heat death, the final equilibrium state. The voids, which started as slightly underdense regions 13.8 billion years ago, have become the entire universe. Everything is void. The distinction between void and structure has vanished, because all structure has dissolved. The cosmos is a cold, dark, expanding vacuum, approaching absolute homogeneity. Time becomes meaningless. Change ceases. The universe exists but nothing happens. This is the standard cosmological model's prediction, assuming the cosmological constant remains truly constant. But alternatives exist. If dark energy is not constant, the future could be different. If dark energy density increases, expansion accelerates faster. This could lead to the Big Rip, where expansion becomes so violent that it tears apart bound structures. First galaxy, clusters unbind, then galaxies, then solar systems, then planets, eventually atoms and nuclei. The universe ends not in cold darkness, but violent disintegration. If dark energy density decreases, expansion might slow. If it decreases enough, expansion could reverse. The universe would begin contracting, the big crunch. Galaxies would start moving together instead of apart. Voids would shrink. The cosmic microwave background would heat up. Eventually everything would merge into a singularity. The big crunch is the time reversal of the Big Bang. The universe ends where it began, in infinite density. Current observations favour a cosmological constant, implying heat, death, but measurements have uncertainties. The future is not certain. It depends on dark energy's true nature, which remains unknown. Whether the universe ends in heat death, Big Rip, or Big Crunch is an open question. But all three scenarios share one feature. The voids grow and empty. Structure dissolves. The distinction between void and galaxy region blurs and vanishes. The far future is also affected by quantum effects. In a de Sitter universe with a cosmological constant, vacuum fluctuations can create Boltzmann brains. These are random fluctuations that briefly assemble consciousness before dissipating. In infinite time, any finite probability event occurs infinitely many times. Conscious observers spontaneously appearing from vacuum fluctuations is unlikely, but not impossible. Given infinite time, it happens infinitely often. This creates a paradox. If Boltzmann brains are inevitable in the far future, then most observers in the universe's history are fleeting fluctuations rather than evolved beings. This seems absurd. It suggests something is wrong with our understanding. Perhaps the universe is not truly eternal. Perhaps it undergoes cycles. Perhaps our cosmological model is incomplete. The Boltzmann brain paradox is one of several hints that heat death might not be the final answer. Alternative theories propose cyclic universes, the big crunches, followed by a big bounce. The universe contracts to a minimum, size, then expands again. This cycle repeats infinitely. Each cycle might be similar or different. The voids in one cycle seed the structures of the next, or information is erased at each bounce. Cyclic models avoid the infinite past problem and the Boltzmann brain problem, but they face other difficulties, including how bounces occur and what determines cycle properties. String theory suggests other possibilities. The landscape string vacua contains perhaps 500 different vacuum states. Our universe exists in one such state. Quantum tunneling can transition between states. If this happens, a bubble of new vacuum forms and expands. Inside the bubble, different physics apply, different constants, different particles, different forces. The bubble wall sweeps through space at light speed, converting our vacuum to the new one. This is vacuum decay, a different kind of end. If vacuum decay occurs, the future of voids is sudden. Transformation. A bubble nucleates somewhere, perhaps in a distant galaxy or perhaps in deep void space. The bubble expands at light speed. We cannot see it coming. When the wall reaches us, our atoms are disassembled. New physics takes over. What happens inside the bubble depends on the new vacuum's properties. It might be incompatible with any structure, or it might allow different kinds of structures. We cannot predict. Vacuum decay could happen tomorrow or never. The probability is incalculable with current knowledge. If our vacuum is truly stable, it never occurs. If metastable, it eventually happens. The timescale could be billions of years or Googleplex years. We have no way to determine which. This uncertainty adds a different kind of unpredictability to the future. Not just evolution, but possible phase transition. Despite these uncertainties, some predictions are robust. The voids will continue growing as long as dark energy drives expansion. Galaxies will continue separating. The observable universe will shrink as more regions cross the cosmic event horizon. The temperature of space will continue decreasing as the cosmic microwave background redshifts. These trends are observationally confirmed and theoretically solid. They will continue unless physics changes drastically. The future of voids is therefore mostly certain in the near term. Billions to trillions of years, they expand and empty. But in the far future, beyond 10, 15 years, uncertainties dominate. We do not know if protons decay, if black holes are truly stable, if dark energy is constant, if vacuum decay occurs, if quantum fluctuations create new structures. The equations give multiple possible futures. Observations cannot yet distinguish between them. What this reveals is that understanding voids requires understanding the deepest laws of physics. The space between galaxies seems like the simplest, most boring part of the crease. Universe, just empty space. But its future depends on dark energy, quantum gravity, the stability of matter, and the topology of vacuum states. These are frontier problems where theory remains incomplete. The voids are testing grounds for fundamental physics. The fate of the voids is the fate of space itself. They are the purest form of space, minimally corrupted by matter and structure. How they evolve reveals how space evolves. Whether they expand, forever, or collapse or transform tells us whether the universe is eternal, cyclic, or unstable. The vast empty regions between galaxies are not irrelevant backgrounds. They are the substrate on which everything else rests. Their future is the universe's future. And so the question of what lies between galaxies opens onto the largest questions. What is space? What is vacuum? What is the ultimate fate of reality? These questions have no final answers yet, but studying the voids provides clues. Every measurement of void properties, void evolution, void temperature, void expansion rate contributes data. The darkness between galaxies speaks, quietly but clearly, about the nature of existence itself. The living web. The space between galaxies might seem sterile. No stars means no heat. No planets means no environments for life. The emptiness should be dead. But this assumption might be wrong. Life, as we know, it requires specific conditions. But life, as we don't know it, could exist in environments we consider impossible. The cosmic voids might not be as lifeless as they appear. Consider extremophiles on Earth. These organisms thrive in conditions that seem hostile to life. Bacteria live in boiling hot springs at temperatures exceeding 100 degrees Celsius. Others to survive in Antarctic ice at temperatures below -20 degrees. Some metabolize sulfur instead of oxygen. Others withstand radiation, doses that would kill humans instantly. Life adapts to extreme environments routinely. It finds ways to extract energy from unlikely sources. If life exists between galaxies, it would face different challenges than life on planets. No solid surfaces, no liquid, water in most regions, extremely low densities of matter, intense radiation in some areas, especially near the cosmic webs, filaments, temperatures ranging from millions of degrees in clusters to a few Kelvin in voids. These conditions seem incompatible with chemistry complex enough to support life. But consider the hot gas in galaxy clusters. The intracluster medium contains carbon, oxygen, nitrogen, and other biologically important elements. The temperature is millions of degrees, but the density is extraordinarily low. In such plasma, atoms are completely ionized. Complex molecules cannot form, but individual ions interact through electromagnetic forces. Could some form of organization arise? Could patterns in plasma constitute a form of life? This is speculative physics, not science fiction. Plasma can self-organize into structures called dusty plasmas. When dust grains exist in plasma, they become charged. The charged grains interact, forming ordered structures, hexagonal lattices, chains, even helical patterns appear spontaneously. These structures are driven by energy gradients in the plasma. They maintain themselves against dissipation. They exhibit properties analogous to crystals, but in a completely different medium. Could such structures evolve? Could they replicate? Could they store and transmit information? These questions have no answers yet, but they are scientifically legitimate. Plasma physics allows for complex self-organization. Whether that organization can reach the threshold of life is unknown. No observations confirm plasma-based life, but no observations rule it out either. The diffuse gas in filaments and voids offers different possibilities. This gas is cold, only thousands of degrees. Neutral atoms exist. Simple molecules can form. Hydrogen molecules, H2, are the most common. Carbon monoxide, water, and more complex organics might exist in trace amounts. The densities are extraordinarily low, 1 atom per cubic meter in voids. But integrated over millions of light years, substantial masses of material exist. In interstellar space, within galaxies, complex organic molecules have been detected. Polycyclic aromatic hydrocarbons, amino acid, precursors, even sugar molecules. These form on dust grains, where atoms can meet and bond. Could similar chemistry occur in intergalactic space? The dust density is lower, but non-zero. Metal-enriched gas from galactic winds contains dust grains. These grains could catalyze reactions just as in interstellar clouds. The timescales are different. In molecular clouds, molecules form over millions of years. In intergalactic space, the process would to be slower. Perhaps billions of years to build complex chemistry. But the universe is old. Time is available. If molecular complexity can develop, could it lead to life? Could self-replicating molecules arise in the diffuse medium between galaxies? This seems extremely unlikely, but not impossible. Life on Earth probably originated in the ocean, where molecules concentrated in a small volume. The intergalactic medium's low density makes concentration difficult, but local enhancements exist. Shock fronts in colliding gas flows could compress material. Magnetic fields could funnel ions along field lines. Small-scale structures could create temporary, high-density regions where chemistry accelerates. Another possibility is panspermia on cosmic scales. Life originated on planets, but microorganisms could be ejected by asteroid impacts or stellar winds. These microorganisms, in dormant states, could survive in interstellar space. Some might escape their host galaxies and enter intergalactic space. There, they could drift for millions or billions of years before encountering another galaxy. The survival of microorganisms in space has been tested. Bacterial spores can survive vacuum, radiation, and extreme temperatures for years in laboratory conditions. Tardigrades, microscopic animals, have survived exposure to space on the exterior of the International Space Station. If such organisms can survive short-term space exposure, could they survive long-term transit through intergalactic space? The main threat is radiation. Cosmic rays would bombard any organism continuously. Over millions of years, the accumulated dose would destroy all known biological molecules. DNA would be shredded. Proteins would be degraded. No known shielding is sufficient except thick rock. An organism inside a meteoroid might survive. But meteoroids are rare in intergalactic space. Most ejected material is dust grains, too small to provide shielding. However, radiation-resistant extremophiles exist on Earth. Deinococcus radiodurans can repair DNA damage from radiation doses, thousands of times higher than what would kill humans. If such resistance mechanisms were enhanced through evolutionary pressure, perhaps organisms could survive intergalactic transit. This is purely speculative, but not forbidden by physics. If panspermia operates on cosmic scales, then life could be distributed throughout the universe, not just within galaxies, but between them. The voids might contain dormant life, frozen time, waiting to encounter a new world. This would mean the space between galaxies is not dead but sleeping, a reservoir of potential life spreading across the cosmos. Exotic possibilities also exist. If dark matter can interact with itself through forces other than gravity, complex dark matter structures might form. Dark matter chemistry. Dark matter molecules. If these can organize into self-replicating patterns, then dark matter life becomes conceivable. This life would be completely invisible to us. It would not interact electromagnetically. We could not detect it except through gravitational effects. This is wild speculation, but dark matter comprises 85% of matter. If even a small fraction of dark matter participates in complex interactions, the implications are staggering. The space between galaxies is filled with dark matter, more dark matter than ordinary matter. If that dark matter is alive, then the voids are teeming with life we cannot see. Current dark matter models do not support this. The leading candidates, WIMPs and axions, interact only weakly. They do not form molecules or structures beyond gravitational clumping. But the dark matter problem is unsolved. We do not know what it is. Future discoveries might reveal unexpected properties. If dark matter has a rich sector of particles and forces, complexity becomes possible. Even without exotic life forms, the space between galaxies plays a role in the origin of life. The chemical elements necessary for life were created in stars: carbon, nitrogen, oxygen, phosphorus, all formed through nucleosynthesis in stellar cores and supernovae. These elements were expelled into space through stellar winds and supernova explosions. They mixed with the intergalactic medium, enriching it. This enriched gas later fell into new galaxies, where it formed new stars and planets. The second and third generation stars had more heavy elements than the first generation. Their planets could be rocky rather than just gaseous. The chemistry on those planets could be more complex. Life became possible only after the intergalactic medium had been enriched with metals. In this sense, the space between galaxies is part of life's origin story. The elements in your body were created in stars, expelled into intergalactic space, and eventually incorporated into the solar system. You are made of material that has travelled through intergalactic space. The voids are not separate from life. They are part of the system that produces life. The cosmic web itself might influence where life arises. Galaxies, in dense regions like clusters, experience frequent interactions. Mergers, tidal disruptions, and high-energy radiation might disrupt planetary systems. Galaxies in filaments are more stable, but still interact occasionally. Galaxies in voids are most isolated. They evolve quietly without major disturbances. This stability might favour the long-term evolution of complex life. But void galaxies are metal poor compared to cluster galaxies. They have fewer heavy elements. Their planets might be less favourable for life. The balance between stability and composition is unclear. Perhaps intermediate environments, in filaments rather than voids or clusters, are optimal for life. This is testable in principle. By searching for biosignatures in exoplanet atmospheres, in different cosmic environments, we might determine where life is. Most common. The search for extraterrestrial intelligence, SETI, also relates to intergalactic space. If advanced civilizations exist, they might attempt communication across galactic distances. Radio. Signals could propagate through intergalactic space for millions of years. A beacon placed in a central galaxy cluster could potentially reach thousands of galaxies in its local region. Civilizations could create an intergalactic communication network. Such a network would face challenges. Signal strength decreases with distance. Galactic radio emission creates noise. The time. Delays are millions of years, preventing real-time conversation. But for information exchange, these challenges might be acceptable. A sufficiently advanced civilization could use massive power sources to create detectable signals. Pulsed lasers or beamed radio waves at specific frequencies could cut through background noise. If intergalactic communication exists, we might detect it eye. Searches typically focus on our galaxy, but some surveys search other galaxies too. So far, no convincing signals have been found. This could mean intelligent life is rare, or it could mean we are looking incorrectly, or civilizations exist but choose not to broadcast. The absence of evidence is not evidence of absence. Some have proposed that advanced civilizations might use the cosmic web itself for communication. The filaments connecting galaxies could act as waveguides for signals, or civilizations might place relay stations along filaments, maintaining an intergalactic internet. This is pure speculation, but it illustrates how life, if it exists at cosmic scales, might utilize the structure of intergalactic space. The living web might not be biological at all. It might be technological. Self-replicating probes could spread through galaxies and beyond. These von Neumann probes would build copies of themselves from local materials. They could explore the universe, transmit data back to their creators, and continue spreading. Over millions of years, such probes could fill intergalactic space. Why haven't we seen them? This is the Fermi paradox applied to intergalactic space. If self-replicating probes are possible, advantageous, they should exist, yet we observe none. Possible explanations include that advanced civilizations do not build them, that they do but remain undetectable, that we are the first, or that some great filter prevents civilizations from reaching the probe-building stage. The question of life in intergalactic space connects to the deepest questions about life itself. What is life? Is it chemistry, information processing, self-replication, metabolism? Different definitions give different answers about what is possible in extreme environments. If life is fundamentally information patterns that maintain themselves against dissipation, then many substrates might support it. Not just water and carbon, but plasma, quantum fields, or even space-time geometry. These ideas remain speculative because we have only one example of Earth. We do not know which features are necessary and which fear are incidental. Carbon chemistry might be essential, or it might be just one possibility among many. Until we find a second origin of life, we cannot generalize. But the question is scientifically important. If life can arise in intergalactic space, the implications transform our understanding of biology and cosmology. The universe might be far more alive than it appears. The darkness between galaxies might harbour ecosystems we cannot yet imagine, or it might be truly sterile, emphasizing how special and fragile planetary life is. Either answer teaches us something. If life exists only on planets, we learn that biology requires specific, rare conditions. Earth-like worlds are precious. We should value and protect them. If life exists everywhere, even in voids, we learn that biology is fundamental. Life is not a rare accident, but an inevitable consequence of physics. The universe itself is alive in some sense, continuously generating complexity. The living web remains hypothetical. No evidence confirms life between galaxies. But no evidence rules it out either. As our technology improves and our understanding deepens, we might discover biosignatures in unexpected places. Or we might confirm that the space between galaxies is truly lifeless. Either discovery would be profound, Both would reshape how we see ourselves in the cosmos. The voids, the filaments, the cosmic web, all might be more than passive structure. They might be habitats, environments, ecosystems, or they might be exactly what they appear, empty space, where matter and energy obey simple physical laws. The question remains open. The darkness between galaxies keeps its secrets, and we, bound to our small planet, continue to wonder what truly exists in the vast spaces beyond. The measurement problem. Studying what lies between galaxies is extraordinarily difficult. The signals are weak, the distances are vast, the densities are low. Every observation pushes technology to its limits. Understanding these challenges reveals not just technical issues, but fundamental constraints on knowledge itself. The primary challenge is brightness. Galaxies contain billions of stars. They shine brightly enough to detect across billions of light years. The space between them contains diffuse gas at densities millions of times lower than the best laboratory. Vacuums. This gas emits faint radiation. Detecting it requires instruments far more sensitive than needed for galaxies. X-ray observations illustrate the problem. Galaxy clusters emit strong X-rays from their hot intracluster medium. Modern X-ray telescopes like Chandra and XMM Newton detect them easily, but the warm, hot intergalactic medium in filaments is 10 to 100 times less dense. Its X-ray emission is correspondingly fainter. Current instruments barely detect it, confirming its existence. Requires long exposures and sophisticated background subtraction. The WIM, as it's called, contains most of the ordinary matter in the universe, but it radiates so weakly that mapping its distribution is nearly impossible with current technology. Future X-ray missions with larger collecting areas and better spectral resolution are planned, but even these will struggle to detect the WIM comprehensively. The fundamental limit is photon counting. Statistics. Faint sources produce few photons. Noise dominates the photons. Signal. Radio observations face similar issues. Neutral hydrogen in intergalactic space can be detected through its 21 centimeter emission line, but the brightness is extremely low. Radio. Telescopes must integrate for many hours to detect anything. Even then, the signal is barely above noise. Proposed radio arrays like the Square Kilometre Array will improve sensitivity dramatically, but even SKA will detect only the densest intergalactic gas. Deepest voids will remain invisible. Absorption spectroscopy works better because it does not rely on faint emission. Light from a bright background source passes through intervening gas. The gas absorbs at specific wavelengths, creating dark lines in the spectrum. This technique has revealed the Lyman alpha forest and metal absorption systems. It works well for gas along the line of sight to quasars, but it samples only one-dimensional slices. Building three-dimensional maps requires observing many quasars in different directions. The number of suitable background sources is limited. Quasars are rare and require large telescopes to observe. Gamma-ray bursts are brighter, but even rarer and unpredictable. Fast radio bursts are numerous, but difficult to localize precisely. Each source type has limitations. Comprehensive mapping of intergalactic gas remains beyond reach. Gravitational lensing offers a powerful alternative. Mass bends light regardless of whether that mass emits radiation. Lensing maps reveal the total matter distribution, including dark matter. Weak lensing surveys have mapped the cosmic web across large areas, but lensing has limited resolution. It cannot resolve structures smaller than roughly 1,000,000 light-years. Voids are detectable, but not their internal structure. Strong lensing provides higher resolution, but only for rare, well-aligned systems. Multiple images of background sources reveal the foreground mass distribution in detail. This technique has mapped individual galaxies and galaxy clusters precisely, but it requires fortunate alignment. Most intergalactic space is not accessible through strong lensing. Microlensing can detect smaller objects. When a compact mass passes in front of a background star, it briefly magnifies the star's light. This technique has detected planets, brown dwarfs, and black holes in our galaxy. Applying it to intergalactic space would require monitoring millions of stars in other galaxies continuously. The event rate is low, but future surveys might attempt this, searching for rogue planets or primordial black holes drifting in intergalactic space. Another challenge is resolution. Astronomical images have angular resolution measured in arcseconds or milliarcseconds. This angular size corresponds to different physical sizes, depending on distance. An arcsecond at 1 billion light-years spans about 5,000 light-years. Structures smaller than this cannot be resolved. The cosmic web's filaments are barely resolvable at large distances. The subfilament structure is invisible. Interferometry improves resolution by combining multiple telescopes. Radio interferometers like the Very Large Array and ALMA achieve milliarcsecond resolution. Optical interferometers are being developed, but interferometry requires precise coordination between telescopes. It works best for point sources or simple structures. Extended diffuse emission, like intergalactic gas, is difficult to image interferometrically. Time resolution also matters. The universe evolves, structures change. To study evolution, we must observe the same regions at different cosmic times. This means looking at different distances, since looking farther means looking back in time. But observing a high redshift structures is harder because they are fainter and smaller in angular size. Balancing depth and clarity is challenging. Spectral resolution determines how precisely we can measure wavelengths. High spectral resolution reveals detailed absorption, line profiles, temperature, density, velocity structure. But achieving high resolution requires spreading light across many detectors, reducing sensitivity. There is always a trade-off: high spectral resolution with low sensitivity, or low spectral resolution with high sensitivity. The optimal choice depends on the science question. Systematic errors plague measurements. Telescopes introduce artifacts. Detectors have noise patterns. Atmospheres scatter and absorb light. Correcting for these effects requires careful calibration. But calibration is imperfect. Residual errors remain. When studying faint signals like intergalactic gas, even small, systematics can mimic or hide the real signal. Foreground contamination is particularly troublesome. Light from our own galaxy fills the sky. Emission from interstellar gas, zodiacal dust, and stars creates backgrounds that must be subtracted. But these foregrounds are not uniform, they vary across the sky. Removing them without removing the faint intergalactic signal is delicate Over subtraction loses signal. Under subtraction leaves contamination. Cosmic variance is another issue. The universe is not uniform on all scales. Random fluctuations mean that different regions differ. Observing a small area gives results that might not represent the universe as a whole. To overcome cosmic variance requires surveying large volumes. But large surveys are time-consuming and expensive. There is tension between depth, area, and available observing time. Selection affects bias results. We detect what our instruments can see. Bright sources are easily found. Faint sources are missed. This creates the illusion that bright objects are more common than they really are. Correcting for selection effects requires understanding instrument sensitivity precisely. But sensitivity depends on many factors: integration time, wavelength, source, structure. Corrections are uncertain. The theoretical challenge matches the observational challenge. Simulating cosmic structure requires enormous computational resources. The universe contains structure on scales from subatomic to cosmological. Simulating this range is impossible. Simulations must choose a dynamic range. Large-scale cosmological simulations resolve structures down to about 100,000 light-years. They capture the cosmic web but miss the galaxy's internal structure. High-resolution galaxy simulations resolve stars but simulate only small volumes. Bridging these scales is the frontier of computational cosmology. Techniques like adaptive mesh refinement and zoom simulations partially address the problem, but full self-consistent simulations from inflation to individual stars remain beyond capability. This limits theoretical predictions. We can predict statistical properties, but not details. The physics in simulations is also simplified. Real intergalactic gas experiences heating from shock waves, cooling through, radiation, ionization from background radiation, magnetic field, effects, cosmic ray pressure, and more. Including all these processes is computationally prohibitive. Simulations use approximate prescriptions. Subgrid models parameterize unresolved physics. These introduce uncertainties. Different simulation codes give slightly different results. Cosmic web statistics vary by a few percent depending on the code. This reflects numerical errors, different approximations, and incomplete physics. Comparing simulations to observations requires understanding these theoretical uncertainties. Claims about agreement must account for both observational and theoretical error bars. Data volume is becoming a challenge. Modern surveys generate terabytes of data. Upcoming surveys will produce petabytes, storing, processing, and analyzing. This data requires infrastructure. Machine learning techniques are increasingly used to identify patterns and classify sources. But machine learning introduces new systematics. Algorithms must be trained carefully to avoid biasing results. The human element matters too. Interpreting data requires judgment. Deciding what is signal and what is noise involves subjective choices. Publication bias favors positive detections over null results. This can create false impressions about how common phenomena are. Addressing these issues, transparency, reproducibility, and diverse perspectives, despite all challenges, progress is steady. Each new telescope extends reach. Each new algorithm improves analysis. Observations from decades ago that seemed marginal are now confirmed. The cosmic web, once hypothetical, is now mapped in detail. The intergalactic medium, once invisible, is now characterized. The trajectory is clear. What seems impossible today becomes routine tomorrow. Future facilities promise transformative gains. The James Webb Space Telescope observes at infrared wavelengths, detecting redshifted light from the first galaxies. Its sensitivity reveals faint structures in the early universe. The Vera Rubin Observatory will survey the entire visible sky repeatedly, tracking transients and measuring billions of galaxies for weak lensing. The extremely large telescopes, with mirrors 30 to 40 meters across, will collect enormous amounts of light, enabling spectroscopy of faint sources. Space-based missions avoid atmospheric absorption and scattering. Future X-ray telescopes, like Athena and Lynx, will detect the WIM comprehensively. Far infrared missions will trace dust and gas in galaxies and in intergalactic space. Radio facilities in space or on the far side of the moon will observe frequencies blocked by Earth's ionosphere. Multi-messenger astronomy opens new channels. Neutrino detectors and gravitational wave observatories complement electromagnetic observations. Each messenger provides independent information. Together, they create a comprehensive picture. The Ice Cube Neutrino Observatory already extragalactic sensitivity sources detects future high energy facilities. Neutrinos will from increase, combining datasets from multiple wavelengths, multiple messengers, and multiple epochs creates synergies. The whole exceeds the sum of parts. Patterns invisible in single datasets emerge when data are combined. This requires careful cross-calibration and sophisticated statistical techniques, but the payoff is profound. The measurement problem, though difficult, is not insurmountable. What these measurements ultimately reveal is that the space between galaxies is observable. It is not forever hidden. Every property discussed, gas density, temperature, dark matter, distribution, magnetic fields, can be measured. The measurements are challenging but doable. Each generation of instruments brings clarity. The darkness reveals itself through patient, careful observation, and this reveals something fundamental about science. Knowledge is possible. Reality, though distant and faint, can be probed. The universe is intelligible. Limits exist, but they are not absolute. They recede as technology advances. What lies between galaxies was once completely unknown. Now it is partially known. Tomorrow it will be better known. The trajectory points toward comprehensive understanding, though complete knowledge may remain asymptotic. The measurement problem is not just technical, it is philosophical. It asks, how do we know what we know? How certain can we be? What does it mean to understand something we cannot directly visit or touch? These questions apply not just to intergalactic space, but to all science. The answers shape how we interpret data and how confidently we claim knowledge. Studying what lies between galaxies therefore tests the scientific method itself. It pushes instruments to their limits. It demands creativity in observation and analysis. It requires collaboration across disciplines, and it forces humility about what can and cannot be known. The space between galaxies is not just a scientific subject. It is a crucible where science refines itself, learning how to extract truth from faint signals in the darkness. The philosophy of emptiness. What does it mean for space to be empty? The question seems trivial, but is not. Emptiness is not absence. It is the presence of space without matter. But space itself is something, not nothing. This distinction matters philosophically and physically. Understanding emptiness reveals assumptions underlying physics and epistemology. In everyday language, empty means containing nothing. An empty bottle has no water. An empty room has no furniture. But the pack bottle still contains air. The room contains electromagnetic radiation, neutrinos, and gravitational fields. Truly empty means containing literally nothing. No particles, no fields, no energy. This is vacuum. But quantum mechanics says a perfect vacuum is impossible. The uncertainty principle forbids fields from having zero energy. Fluctuations are unavoidable. The vacuum state is the lowest energy configuration, but it is not energyless. Virtual particles pop in and out of existence. The vacuum hums with activity at quantum scales. Empty space is quantum foam. This changes the meaning of emptiness. The space between galaxies is not nothing. It contains quantum fields in their ground state, plus sparse matter and radiation. Describing it as empty is an approximation. Useful approximation, but still approximate. Philosophically, this suggests that absolute nothingness might not exist. Even the most empty regions of space-time have structure and content. Some philosophers argue that space itself is relational rather than absolute. Space does not exist independently. It is defined by relationships between objects. Without objects, there is no space. This view, called relationism, contrasts with substantivalism, which holds that space is a thing in itself. Substantivalists say space would exist even if nothing occupied it. Relationists disagree. General relativity is sometimes interpreted as supporting relationism. Space-time geometry is determined by matter and energy through Einstein's field equations. But empty space has geometry, too. The solution to Einstein's equations with zero matter is flat, Minkowski spacetime, or de Sitter spacetime, if vacuum energy exists. This suggests space exists independently of matter. The debate continues. The cosmic voids provide a test case. If space is relational, do voids exist? They contain almost no matter. The sparse gas and dark matter are negligible. If relationships between objects define space, then void space is barely defined. Yet we observe voids. They have measurable properties. They expand. They have temperatures. This seems to favor substantivalism. Space exists there even without significant matter. But relationists can respond. The voids are defined by their boundaries. The surrounding galaxies and filaments establish a coordinate system. Within that system, the void occupies a region. Without the boundaries, we could not identify or measure the void. So even voids are ultimately relational, defined by contrast with denser regions. The philosophical debate might seem academic, but it affects how we interpret cosmology. If space is absolute, the Big Bang created space itself. Before the Big Bang, nothing existed, not even space or time. If space is relational, the Big Bang created matter, energy that defines spatial relationships. The distinction shapes what counts as an explanation. The concept of empty space also relates to the infinite. If the universe is infinite, it contains infinite space, infinite volume. But can infinity be physically real? Mathematically, infinity is well defined. Physically, it creates puzzles. If space extends infinitely, there are infinitely many galaxies, infinitely many stars, infinitely many atoms. This bothers some physicists who argue physical quantities should be finite, but others point out that infinity appears naturally in theories. Infinite space is the simplest solution to Einstein's equations, with zero curvature. Rejecting it requires adding complexity. Perhaps infinity is real. Perhaps the universe is not just very large, but literally infinite. The voids extend endlessly in all directions. This is philosophically unsettling, but not logically contradictory. The void also raises questions about properties. Does empty space to have properties? Temperature, energy, density, curvature. These are properties we measure. But are they intrinsic to space or accidents of matter and fields? If we removed all matter and energy from a region, would space there have properties? General relativity says yes. Space-time has geometric properties, independent of matter content. The metric tensor describes these properties. Even empty space has a metric. It can be flat or curved. This intrinsic geometry is a property of space-time itself, not of what occupies it. So empty space has properties. But quantum field theory complicates this. The vacuum state of quantum fields carries energy. This vacuum energy contributes to space-time curvature. It is why dark energy exists. So the properties of empty space depend on quantum fields. Without fields, would space have properties? This question is unanswerable. Because we cannot remove fields, they are fundamental. Space without fields might not be a coherent concept. The relationship between space and fields is thus subtle. Are fields substances occupying space? Or are they features of space itself? The history of physics shows evolution in thinking. Classical physics treated fields as substances in space. Relativity unified space and time into space-time quantum field. Theory made fields fundamental. Space might be emergent from field properties rather than the other way round. Some modern theories take this seriously. Loop quantum gravity proposes space is discrete networks of quantum states. String theory suggests space emerges from relationships between strings. Emergent space proposals say space-time is not fundamental but derived from something deeper. If space is emergent, then asking about empty space is like asking about empty chess games. The concept does not apply. Space only exists where the underlying quantum structures create it. These ideas remain speculative, but they illustrate that emptiness is not simple. Our intuitions, shaped by everyday experience, mislead us at fundamental levels. Space, vacuum, emptiness, all require careful definition. The void between galaxies seems like the easiest place to study these concepts, but it turns out to be subtle. Existentially, emptiness resonates with ancient philosophical and spiritual traditions. Buddhist philosophy emphasizes shunyata, emptiness, not nihilistic absence, but recognition that things lack independent existence. Everything is interdependent. This mirrors relationalist views of space. Space does not exist independently. It is defined by relationships. Western philosophy also wrestles with nothing, Heidegger wrote, about nothingness as fundamental to being. Sartre explored the experience of the void. These existential questions connect, perhaps unexpectedly, to cosmological ones. When we ask what exists in the space between galaxies, we are also asking, what does existence mean? What is the nature of absence? The voids are mirrors. They reflect back our questions. Do they contain something or nothing? Are they empty or full? Are they real or relational? The answers depend on definitions, on theories, on perspectives. No single answer captures the truth. The voids are empty of galaxies, but full of fields. They are nothing compared to clusters, but something compared to a true vacuum. They exist as regions, but derive meaning from boundaries. This multiplicity of perspectives is not a weakness, it is rich. Reality has layers. Different descriptions capture different aspects. The voids can be studied through physics, measuring densities and temperatures. They can be contemplated through philosophy, questioning the nature of space and existence. They can be experienced through awe, standing under a dark sky and pondering the vast dark spaces between pinpoints of light. Each approach reveals the truth. None is complete. Together they form a fuller picture. The space between galaxies is not just a scientific problem. It is a human problem. We are pattern-seeking, beings trying to understand absence. We are material creatures, trying to grasp emptiness. The voids challenge us because they resist simple categorization. They are the in-between, the negative space, the pause between notes of understanding the voids, therefore, requires integrating multiple kinds. Knowledge, physical, measurements provide data. Mathematical models provide structure. Philosophical analysis provides clarity. Aesthetic appreciation provides perspective. None alone suffices. The fullest understanding comes from bringing them together. And ultimately, studying the voids changes how we see fullness. Galaxies are not independent objects floating in nothing. They are condensations in a cosmic web, nodes in a network. The voids define the galaxies as much as galaxies define the voids. Structure and emptiness are complementary. You cannot have one without the other. The universe is not galaxies plus voids. It is a unified system where both are necessary aspects of one pattern. This insight applies beyond cosmology. In any complex system, the gaps matter as much as the components. In music, silence shapes sound. In art, negative space defines form. In language, pauses convey meaning. The voids between galaxies are the cosmos's negative space. They are not mere background. They are integral to the composition. The philosophy of emptiness leads back to physics with renewed appreciation. Measuring void properties is not just cataloguing blank space. It is understanding the structure that makes galaxies possible. Studying the absence reveals the presence, the darkness illuminates the light. The space between galaxies, rather than being nothing to discuss, turns out to be everything. It is where the deepest questions lie, the answer in the darkness. We began by asking what lies between galaxies, after exploring architecture, substance, temperature, light, connections, future, life, measurement, and philosophy. We can now answer the space between galaxies contains everything and nothing. It is the cosmic web's scaffolding. It is quantum vacuum plus sparse matter. It is cold near CMB temperature, hot in clusters. It is curved by mass, stretched by expansion. It is crossed by radiation, particles, and waves. It might harbour life or be sterile. It is observable through effort. It is empty by some definitions, full by others. This multiplicity of answers reflects reality's complexity. The universe does not fit simple narratives. What exists between galaxies cannot be reduced to one statement. It requires context, specification, and nuance. Different aspects require different descriptions. All are true simultaneously. The cosmic void is not void. This is the fundamental revelation. The negative space of the universe has positive content. Structure, fields, energy, history. The gaps between galaxies are not breaks in reality but continuations of it. The same physics operates there as in galaxies. The same fields permeate it. The same space-time contains it. What makes the intergalactic medium special is not that it is empty, but that it is underdense. The average matter density is lower than in galaxies by factors of millions. This underdensity creates different conditions. Gravity is weaker. Gas does not. Collapse into stars. Temperature and pressure are lower. But these are quantitative differences, not qualitative ones. The voids are not different kinds of space. They are the same space with different contents. Understanding this transforms cosmological thinking. The universe is not discrete galaxies separated by nothing. It is a continuous medium with varying density. Galaxies are peaks in the density. Voids are troughs, but the field is everywhere non-zero. Even the deepest voids contain matter, fields, and energy. The continuum is unbroken. This continuum connects everything. Gas flows from voids to filaments to clusters. Gravitational forces extend across voids. Radiation propagates through them. The cosmic web is an integrated system. Every part affects every other part. The voids are as necessary as the structures. Remove them and the entire pattern collapses. Studying what lies between galaxies has thus taught us about interconnection, about how complex structures emerge from simple laws, about how absence and presence define each other, about how questions that seem simple, what is in empty space, open onto deepest physics and philosophy. The darkness between galaxies is not an absence of subject matter. It is an invitation to think comprehensively about the cosmos. And the exploration continues. Every new observation adds detail. Every new theory adds understanding. The questions are not exhaustive. How does the intergalactic medium evolve? What is dark energy? Does dark matter have substructure? Can life exist in extreme environments? How do we observe the unobservable? These questions drive current research. Their answers will reshape our picture yet again. The darkness between galaxies holds secrets still, but those secrets are yielding to investigation. Each decade brings clearer pictures. The cosmic web, mapped in increasing detail. The crazed intergalactic medium, characterized with growing precision. Dark matter, constrained by better observations. Dark energy, probed through void properties and expansion measurements. The trajectory points toward understanding, not complete. Understanding, perhaps never that, but substantive understanding, knowledge grounded in observation and tested by experiment. The space between galaxies will always hold mysteries, because it connects to the deepest unsolved problems. What is dark matter? What is dark energy? What is the ultimate fate of the universe? These questions cannot be answered without understanding intergalactic space. But progress is real. We know more today than yesterday. We will know more tomorrow than today. The voids reveal themselves. Gradually, reluctantly, but genuinely. Each photon detected, each spectrum analyzed, each simulation completed adds pieces to the puzzle. The picture emerges from darkness into light. And perhaps that is the deepest lesson. The darkness is not permanent. It is not impenetrable. It is not empty of meaning or content. The space between galaxies, which appears from Earth as simple blackness, contains multitudes, structure and history, energy and evolution, connections and consequences. The universe's past, present, and future. Understanding what lies between galaxies means understanding the universe itself. The voids are not peripheral, they are central. They contain most of the space. They shape cosmic evolution. They will determine the ultimate fate of everything. Studying them is studying existence at the largest scales. The cosmic void explained is the cosmos explained. The space between galaxies is not background. It is in the foreground. It is where the universe's story unfolds in its purest form. Uncluttered by stars and planets, the fundamental processes operate clearly. Gravity, expansion, dark energy, the interplay of matter and space across billions of years. When you look up at the night sky and see darkness between the stars, you are seeing the universe as it mostly is, not bright pinpoints but dark expanses, not concentrated matter but diffuse fields, not isolated structures but connected webs. The darkness is the default. The light is the exception. And that darkness, when examined closely, reveals itself to be anything but empty. It seethes with quantum fluctuations. It carries ancient photons from the universe's birth. It expands under dark energy's push. It contains sparse atoms forged in stellar cores. It bends passing light with dark matter's gravity. It evolves over cosmic time toward an unknowable future. What lies between galaxies? Everything that matters, everything. that defines the universe's structure and fate. Everything that connects the visible to the invisible, the known to the unknown, the past to the future. The cosmic void is not void, it is cosmos. And understanding it is understanding our place in the vast architecture of reality. The space between galaxies is where the universe truly is, not in the exceptional density of galaxies and stars, but in the ordinary. Emptiness that fills most of space. That emptiness is the canvas. The galaxies are merely details painted upon it. To understand the painting, you must understand the canvas. To understand the universe, you must understand the space between galaxies. And so we return to where we began, looking up at the night sky, seeing the darkness. But now I see it differently, not as absence, but as presence, not as nothing, but as something, not as void, but as substance. The space between galaxies is the universe showing its true face. And that face, when we learn to read it, tells the story of everything.